Metric units of energy are used quite often here in the United States. The metric units of energy, let's talk about several of them. There's the calorie and then there's the calorie. Now these are it's the same word, and the difference is that here's a lowercase c and an uppercase c. And it turns out that the uppercase c calorie is just 1,000 of these lowercase c calories, you see. And really this rascal ought to be a kilocalorie, but it's used so often that they just use the word calorie and put an uppercase C with it. At any rate, there's a kind of a formal definition associated with this calorie. It's the amount of heat required to raise the temperature of 1 kilogram of water 1 degree Celsius. Kind of a fancy definition, and it gives us an idea of the amount of energy required, but we're not going to use the definition very often. By the way, if this calorie is 1,000th of this uppercase C calorie, and if here's a kilogram in this definition, well, let's see, 1,000th of a kilogram would be 1 gram, so would it make some sense that if this calorie is 1,000th of that one, that the definition for the calorie here would be the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. You see, so there is a close relationship to these two. All right, now, so we're going to have problems that involve this calorie idea, and calories are energy units that are referred to when talking about body heat and the amount of energy that is expended exercising and all of that kind of thing, and the number of calories that you get by eating certain foods and whatnot. Okay. Another kind of energy unit related to electricity is the watt hour, and it's designated with an uppercase W and then an H, watt hour. And then the kilowatt hour is related because it's just 1,000 watt hours, and it's kWh. There's a formal definition for watt hour as well. It's the amount of energy required to lift 1 kilogram 370 meters. Again, it's a formal definition. It's not one that we'll refer to often. Let's just realize that this relates to the energy in electricity, and this relates to energy in the body. We can think of it like that. And our problems will be confined in these two areas. We're not going to be converting between these two, so we can get right into some word problems. Swimming uses 480 calories per hour. How many calories are used by swimming a half hour each day for 30 days? A half hour a day for 30 days. Generally, these problems just involve some understanding of the problem and just some rather simple manipulation, just some simple multiplication or addition or something like that. Now, we have, in this idea of 480 calories per hour, to make the calculation of the number of calories used, we need to calculate the total number of hours. Now, it's a half hour each day for 30 days. So, 1/2 hour per day for 30 days is what? Well, a half hour per day for 30 days, 1/2 times 30, oh, that's 15. So 15 hours, you see. So that's a total of 15 hours. Now, we have expended energy at the rate of 480 calories per hour for 15 hours. How do we figure the total number of calories burned? Well, we multiply by the number of calories. So we're going to multiply 15 times 480 calories per hour, and we get this. Now, this should be an uppercase C because there's an uppercase C up there. But when you multiply, and in multiplying this, you find the amount to be 7,200, I believe. 7,200 calories are expended in that exercise. Here's another one. Walking burns 180 calories per hour. How many calories are burned by walking 5 1/4 hours during 1 week? Now, and when it says 5 1/4 hours during 1 week, you see, that's for the whole week. That's not 5 1/4 hours every day for a week. It's just 5 1/4 hours during the whole week. It's really important to be careful in reading these because you tend to think that calculations performed in a previous problem need to be performed in this one. And really that's not the case here. We had to multiply up here a half hour per day times 30 days to get the 15 hours, you see, of the exercise. But here, the total amount of exercise in hours is already given to us, so we don't have that multiplication to perform. All we need to do is multiply 5 1/4 hours times 180 calories per hour. So 5 1/4, well, that can be thought of as 5.25. So hours times 180 calories per hour. I'll put that in here. I'd rather over label than under label. All right, so this is the idea. Now multiplying 5.25 times 180, it turns out to be 945 calories are expended. Now, notice the calories per hour. We can think of the per with a slash here. The hour unit is in a denominator. This hour unit is in a numerator. We can think of those as canceling, and what we have left is the calorie unit. A lot of times we can do this unit analysis like this in problems like this and discover the kind of unit that will appear in the answer. We kind of knew that to begin with, though, I think. 945 calories. Let's go to the next problem. A 150-watt bulb is on for 8 hours. At 8 cents per kilowatt hour, find the cost of the energy used. All right, energy is used 8 cents per, the cost of the energy is 8 cents per kilowatt hour. So we kind of need to know how many kilowatt hours we have in burning this 150-watt bulb for 8 hours. Well, let's see. We have a 150-watt bulb. That's 150 watts for 8 hours. When we multiply those two, we get, let's see, 8 times 150 is 1,200. Now, what's the unit? Well, it's watt hours. Oh, this is what we're after. So we have this 1,200 watt hours are used. But that's not the way the cost is listed. The cost is listed in terms of kilowatt hours. You see, it's so much per kilowatt hour. And so now we have to change this into some number of kilowatt hours. And let's do that. We're going to a larger unit. There are fewer of them. We divide to get fewer. There are 1,000 watt hours in 1 kilowatt hour, so we divide by 1,000. Slide that decimal 3 places over, and this becomes 1.2. And now we take 1.2 kilowatt hours and multiply times the cost per kilowatt hour. That's 8 cents per kilowatt hour. And we get, well, let's see, 8 times 2, 16. 8 and 1 is 9. That's 9.6. So that's 9.6 cents. Now, if we change this into dollars and cents, it's 9.6 cents or 9.6 pennies. We would slide the decimal 2 over and list this with a dollar sign as, let's see, sliding 2 over, I would have 0.96, kind of like this. Okay, and we want to retain these parts of pennies here when we're talking about little pieces of energy consumption like this. This one is about a TV set. It says a TV set rated at 1,800 watts is on for an average of 3.5 hours per day. At 7.2 cents per kilowatt hour, find the cost of operating the set for 1 week. Now, again, the problem seems complicated at first, but we need to dig into it and stay organized in order to flow through the problem well. We need to know first the total number of hours that the TV set is going to be on throughout the whole week. And then we use the information about that 1,800 watts to generate a number in watt hours. And once we have the watt hours, we convert that to kilowatt hours. And then we figure the total cost just by multiplying the cost per kilowatt hour times the number of kilowatt hours. Okay, so the idea was to figure the total amount of time the TV set is on for the whole week. So it's, for 1 week, it's on 3.5 hours per day. So it's 3.5 hours per day times 7 days is, you see it's 7 times 3.5, that's 24.5. So 24.5 total hours. Now, we've got that number of hours, and the TV set is rated at 1800 watts. So we have 24.5 hours times 1800 watts is some number of watt hours. You see, in multiplying here, I've already done the multiplication and I put the answer out to the side, so I'm going to look over and read it. It's 44,100 watt hours. Now, the cost of energy, though, is in terms of kilowatt hours. It's a cost per kilowatt hour. But we have a bunch of watt hours here. Well, we can convert this to kilowatt hours. It's 44,100 watt hours is how many kilowatt hours, you see. And let's see, we're changing from a smaller unit into a larger unit, going to a larger unit, fewer of them, divide to get fewer. There are 1,000 watt hours in 1 kilowatt hour, so we're dividing by 1,000. Divide this by 1,000, slides the decimal 1, 2, 3 to the right, 3 to the left, and we have 44.1 then kilowatt hours. Now, the cost per kilowatt hour is 7.2 cents, so we have 44.1 kilowatt hours times the cost per kilowatt hour. I think I'm going to write this in terms of dollars and cents to begin with, because we have quite a number of kilowatt hours here. And 7.2 cents is this amount of money. And multiplying, we get, let's see, this turns out to be, well, it's a kind of a long decimal here, but it turns out to be $3 and a little over 17 cents. So it's $3.1752 to operate the TV set for a week.